So in this problem, we have a hollow spherical conductor. The radius of this conductor is 3 meters. Let's represent that by using capital R. And our goal is to find the electric field at the center of the sphere. The electric field inside a conductor is equal to 0. In the case of having a cavity or a hole inside the spherical conductor, it's going to be equal to 0 if there's no charge in the center. And we can use Gauss's law to explain that. Gauss's law states that the electric field times the area of the Gaussian surface is equal to the charge enclosed by that surface divided by epsilon sub naught. So let's create a Gaussian surface around the center. So that Gaussian surface has a certain value of area, but there's no charge on that surface. So Q is 0, which means that the product EA is 0. Now A has a finite value, which means E has to be 0. So if there's no charge enclosed by a Gaussian surface, then there's no electric field emanating from that region. So that's it for part A. The electric field is equal to 0 at the center of a hollow spherical conductor if there's no charge placed in the cavity. All of the charge on the conductor spreads out evenly on the surface. These positive charges want to be as far apart as possible from each other, since like charges repel. Now what about part B? What is the surface charge density in this problem? How can we figure that out? Well, the equation that we need is this equation. The surface charge density is the ratio between the charge and the area. The area is basically the surface area of the sphere, which is 4 pi r squared. So we have the charge, it's 20 microcoulombs, or 20 times 10 to the minus 6 coulombs. And the radius of the sphere is 3 meters. So let's go ahead and type this in. So the surface charge density is 1.768 times 10 to the minus 7. And the units are coulombs per square meter. So that's how you can find it. Now what about part C? What is the electric field at a distance 5 meters away from the center? So what's the electric field at this point? So let's use Gauss's law to get the answer. So the electric flux, which is the product of the electric field times the area, it's equal to the charge enclosed by the Gaussian surface divided by epsilon sub naught. So the Gaussian area is represented by this purple sphere with radius r. So the surface area is 4 pi r squared. Now the total charge enclosed by the purple sphere is equal to the charge enclosed by the original sphere, because there's no charge in between. So we don't have to change Q. We can leave it the way it is. So now let's divide both sides by 4 pi r squared. So it's Q divided by 4 pi r squared epsilon sub naught. Now I'm going to rewrite it like this. 1 over 4 pi epsilon sub naught times Q divided by r squared. 1 over 4 pi epsilon sub naught is K. So the electric field is the same as calculating the point charge. It's K times Q divided by r squared. So K is 9 times 10 to the 9. Q is 20 times 10 to the minus 6. And the radius, in this case, is 5. We want to find the electric field 5 meters away from the center. So the electric field is equal to 7,200 newtons per coulomb. So that's how you can find it outside of the hollow spherical conductor. You can treat it as if it's a point charge. Now let's say if we have another hollow cylinder. I'm going to make it bigger this time. And let's say there's a charge at the center. Let's use a negative charge. So we have a negative point charge with a magnitude of, let's say, 8 microcoulombs. And let's say the charge on the spherical conductor, let's say it's 15 microcoulombs. Based on this information, what is the charge on the interior of the spherical conductor and on the exterior of it? And also, how can we calculate the electric field? Let's say at a distance r from the point charge, and at another distance r at the midpoint of the spherical conductor, and also outside of it as well. So let's call this R3, R2, and R1. Let's say R1 is 1 meter, R2 is 3 meters, R3 is 5 meters. Actually, instead of using numbers, we'll just write the generic equation. So what is the charge on the interior of the conductor and on the exterior? So first, let's draw a line to separate the interior part of the spherical conductor and the exterior part. Now, because we have a charge on the inside that's -8, an opposite charge will form on the interior of the conductor, and it's going to be equal in magnitude to this charge. So it's going to be positive 8 microcoulombs. Now the total charge on the sphere is 15. So if 8 rests on the inside, 7 has to rest on the outside, because 8 plus 7 is 15. So in this particular example, we have a positive charge on the inside and on the exterior of the spherical conductor. So now let's talk about how to calculate the electric field. The setup is the same as the last example. If you follow the same process, you'll come with this equation, KQ over R squared. But if you want to go through the process, it's EA is equal to Q enclosed divided by epsilon sub naught. So that's going to be Q divided by 4 pi R squared epsilon sub naught, if you want to use that process, but it's the same as using this equation. Now let's talk about how to calculate the electric field at R1. So you have to ask yourself, if we draw a Gaussian surface at R1, what is the total charge enclosed? The total charge enclosed is the -8 microcoulombs that we see here. So therefore, the electric field at R1 is going to be K times the -8 microcoulombs, which we'll just plug in the magnitude only. So that's 8 times 10 to the minus 6. K is 9 times 10 to the 9. And then whatever R1 is, you just plug it in. So you know how to finish it. Now, if you wish to calculate the electric field at R2, we need to find the total charge enclosed by the Gaussian sphere, which is the yellow line. So we have a charge of -8 plus 8, so the total charge is 0. And if Q is 0, then the E value is 0. Let's call that value E2. So E2 is 0. Now E3 is going to be K times Q, that's the total charge. So these two cancel. The total charge is 7. You can also get that number by adding -8 plus 15. So it's going to be K times 7 times 10 to minus 6 divided by R3 squared. So that's how you can calculate the electric field outside of the hollow conductor if there's a charge on the inside. So you got to find the total charge. You have to add these two values.